Hello everyone, I am Karthik, Assistant Professor of Mathematics, SNS College of Engineering. In this lecture video, I will explain about Gauss Divergence Theorem. Introduction to Gauss Divergence Theorem. The Gauss Divergence Theorem is also known as Gauss Theorem or Ostrogradsky Theorem. It is a fundamental result in vector calculus. It relates the flux of a vector field through a closed surface to the divergence of the vector field within the region enclosed by the surface. Statement of the theorem. Let V be a solid region. Let V be a solid region in space whose boundary S is closed surface with outward unit normal vector n. If F vector is a vector field defined on an open region containing V and S with continuous partial derivatives, then the Gauss divergence theorem states integral f ds equal to volume integral del dot f into dv. Next, interpretation. The left side of the equation represents the flux of the vector field f through the closed surface S. The right side of the equation represents the triple integral of the divergence of f over the volume f. Understanding the divergence of a vector field. Understanding the divergence of a vector field is crucial in many areas. For example, physics, engineering, especially in fluid dynamics, electromagnetism, and heat transfer. The divergence of a vector field at the point gives insight into how much the field spreading out. Divergence of a vector field. The divergence of a vector field f at a point in space measures the flux density of the field. Mathematically, the divergence is denoted by del. Then del dot f equal to dou f by dou x plus dou f by dou y plus dou f by dou z. Positive divergence. When the divergence of a vector field at a point is positive, it indicates that the field is spreading out from that point. That is del dot f greater than 0. Negative divergence. Conversely, when the divergence of a vector field at a point is negative, it suggests that the field is converging towards that point. That is del dot f less than 0. Physical interpretation. Positive divergence. Positive divergence represents a source where the vector field diverges outward, indicating a net flow away from the point. Negative divergence. Negative divergence represents a sink where the vector field converges inward, indicating a net flow toward that point. Illustration of Gauss Divergence Theorem. Consider a vector field f equal to x square, y square, z square. First, we have to calculate the divergence. We know that divergence is del dot f. So, del dot f equal to differentiation of x term with respect to x plus differentiation of y term with respect to y plus differentiation of z term with respect to z. So, finally, we have the answer 2x plus 2y plus 2z. Next, calculate flux through surface S. Then evaluate the surface integral. Then finally evaluate the volume integral and simplify the equation. Applying Gauss divergence theorem in 2D. Consider two-dimensional vector field f, that is f equal to x square, y square, and a closed curve C enclosing region D in the xy plane. First, calculate the divergence, that is del dot f equal to 2x plus 2y. Then calculate the line integral f dr equal to surface integral del dot f into dA. Then evaluate the line integral or evaluate the area integral. Applying Gauss divergence theorem in 3D. Similarly, calculate the divergence and calculate the surface, evaluate the surface integral, evaluate the volume integral. Finally, equate and simplify. Examples using divergence theorem in real world problems. Fluid dynamics. In fluid dynamics, the Gauss divergence theorem is used to relate the flux of fluid through a closed surface. Electromagnetism. In electromagnetism, Gauss law electricity and magnetism is a special case of the Gauss divergence theorem. It relates the electric or magnetic flux through a closed surface to the charge or current density within the enclosed volume. Heat transfer. The Gauss divergence theorem can also be applied in problems related to heat transfer. Conservation laws. The Gauss divergence theorem plays a crucial role in the formulation and analysis of conservation laws in physics and engineering. Limitations and assumption of Gauss divergence theorem. Smoothness of a region, continuity of a partial derivatives, closed and orientable surfaces, regularity and boundary, volume enclosed, homogeneity of the medium, Cartesian coordinate system, conservative vector fields. Finally, the Gauss divergence theorem is a powerful mathematical tool, but it is essential to recognize its limitations and assumptions. Thank you.